This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 6, Lesson 7, Piping, Heat Loss, Domestic Hot Water Recirculation, and Thermal Expansion. Two calculations carry this lesson. First, sizing a domestic hot water recirculation pump. The heat the piping loses, divided by the temperature drop you'll allow. Second, sizing the offset leg of an L-bend, so a hot pipe can grow without tearing out its anchors. Both are one-line handbook formulas fed by handbook tables. We'll run each end to end, then place the Z-bend, the pipe loop, and the forces those bends feed back to the anchors. Concept: piping heat loss is the input. Hot water standing in a long domestic hot water main goes cold between draws. So we run a small pump around a recirculation loop and replace exactly the heat the piping loses. That heat loss is a table lookup, never a derivation. There's a bare steel table, a bare copper table, and, the useful one here, a piping table at 140-degree inlet and 70-degree ambient, giving bare and insulated copper both as BTU per hour per foot and as UA per degree. Read the per foot value, multiply by the developed length of the run, and that's your Q. The same family also prints time needed to freeze water, in hours, by pipe size and insulation thickness. Recognize it as a lookup, and don't try to derive it. Setup: the recirculation loop. Pump capacity equals piping heat loss over 500 times the allowable temperature drop. Capacity in GPM, heat loss in BTU per hour, drop in degrees Fahrenheit. That 500 is the familiar waterside constant, minutes per hour, times pounds per gallon, times water's specific heat. So the formula hands you GPM directly. The drop is what you accept around the loop, and it sets the flow. Our loop is 300 feet of 2-inch insulated copper supply and 200 feet of 1-inch insulated copper return, with a 10-degree allowable drop. Solve: the recirculation pump. Build the heat loss first. Each run's per foot table value times its length, added, about 12,940 BTU per hour. Then divide by 500 times the 10-degree drop, 2.6 GPM. That's the pump. And notice the leverage in the allowable drop. Allow 20 degrees instead of 10, and the flow halves to 1.3 GPM. But the last fixture on the loop now sees water 20 degrees cooler than the heater set point. One correction the waterside course never needed: glycol. Freeze-protected loops run 10 to 50% glycol by mass, and glycol is thicker than water. The handbook's procedure is 3 steps. Size the loop as if it carried water. Read the pressure drop correction factor from the printed chart. Factor against temperature. 1 curve per concentration, running from about 0.8 to 1.6, and multiply. Colder fluid and more glycol push the factor up, and the pump grows with it. Concept: thermal expansion of metal pipe. The table is indexed by temperature and gives linear expansion in inches per 100 feet for carbon steel, 304 stainless, and copper. Every entry is measured from a 0-degree datum. That's why the sub-zero rows are negative. So you never read a single row. Read at the operating temperature, read at the installed temperature, subtract, then scale by run length. From 70 to 200 degrees, carbon steel gives about 1 inch per 100 feet, and copper about 1.5. Growth scales with both the temperature swing and the length of the run, and copper moves roughly 50% more than steel for the same swing, so a copper run needs the longer offset leg. Setup: the L-bend. Anchor a run at A, turn it at B into a leg running down to C. When the long run grows, that short leg has to flex to swallow the growth. The handbook calls it a guided cantilever. The printed relation sizes the leg. Length equals 6.225 times the square root of delta times D, where delta is the thermal expansion or contraction of the long leg in inches, and D is the actual pipe outside diameter in inches. Both inputs go in as inches, and the answer comes out in feet. The coefficient carries that conversion. It applies to continuous butt-welded, seamless, and ERW pipe, and to B88 drawn copper tubing. Solve: size the offset leg. 200 feet of 4-inch carbon steel, installed at 70 and running at 200, grows about 2 inches. Feed that and the 4.5-inch actual outside diameter into the L-bend relation, and the offset leg comes out at about 18.5 feet. The same section prints the force that leg feeds back to the anchor. 12 times the modulus of elasticity, times the moment of inertia, times the deflection of that offset leg, over 1728 times leg length cubed. That 1728 is just cubic inches per cubic foot, forced on you because the leg length is in feet. And since the leg is cubed, a slightly longer leg is a dramatically gentler one. Z-bends, pipe loops, and the forces they generate. An L-bend turns once. A Z-bend offsets between two anchors. And a pipe loop is a dedicated expansion loop. All three absorb growth by bending a leg. Only the geometry and the coefficient change. The Z-bend leg is 4 times the square root of delta times d. And here delta is the anchor-to-anchor expansion, not one leg's growth. Its force is 4,000 pounds per inch, times delta, times diameter over length squared. The pipe loop gives width and height in feet by pipe size and expansion, tied together by width equals L over 5, and height equals twice the width. It takes roughly 200 pounds per diameter inch to deflect. And keep any guide at least an offset length away from the offset. Traps. 4. 1. Delta is a difference of two table rows. The expansion table runs from a 0-degree datum, so reading only the operating row overstates the growth. Subtract the installed row first, then scale by length. 2. D is the actual outside diameter. 4-inch carbon steel pipe is 4.5 inches across, not 4. Use nominal and you undersize the leg. 3. The delta T in the recirculation formula is the allowable drop around the loop, not the supply temperature and not the difference to ambient. And Q is the whole loop, supply plus return. 4. The bend coefficients aren't interchangeable. 6.225 for the L bend with the long legs growth. 4 for the Z bend with anchor-to-anchor expansion. Same square root, different number, and a different delta. Quick recall. Piping heat loss comes off the bare steel, bare copper, or insulated piping tables in BTU per hour per foot, with a UA column when your temperatures differ from the tables. Time to freeze is a lookup only. Recirculation pump capacity is heat loss over 500 times the allowable drop. Thermal expansion is inches per 100 feet versus temperature. Always subtract 2 rows. The L-bend leg is 6.225 times the root of delta times actual outside diameter, and the anchor force falls with the cube of that leg. The Z-bend uses 4 instead, with its own force relation, and the pipe loop has a width and height table. Golden rule, the tables are only inputs. You're graded on the 2 formulas. Next up, Lesson 8. Humidification. We kept water hot and gave the pipe room to grow. Now we put water into the air. We'll work the humidification load. 3 printed equations, 1 for each ventilation case. Natural infiltration, a fixed quantity of outdoor air, and a variable quantity. All turning a humidity ratio rise into pounds of water per hour. Everything's at PEPrepEngine.com. Cheat sheet, work solutions, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepEngine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.